Okay, welcome. So today, the last course officially. So as I said, this course was not really planned initially because in my mind I had I think 12 or 13 lectures. This is one plus because the projects are happening next week. So today will just be a small course, okay, half of an actual lecture. So we should finish around three and something. So what I want to do is essentially not much, uh, nothing too new. So we just do a small recap, very small, of what we did. Take a look back at what we saw. Then what I wanted to do is look a bit at what's happening in artificial life lately. So in a sense, we already did that, right? The last few lectures were on models which were very recent, like 2022, 2021. So here it will be more of a high level overview. And then at the end, I want to say a little bit about our research. So me and the people working the same labs as me concerning Alive. So you get an idea of what we actually do. And afterwards, in the second hour, okay, I think probably there will be not too many questions, but if there are questions, I'll be here to answer either on the project or other stuff that you may have. So the very small and quick recap. So during this course, it was more or less separated into three main sections. So there was the first one, which was much more theoretical, and the goal of this section was kind of to understand some rigorous results about self-reproduction, right? That's really what everything we did was, the goal of everything we did was. And through this, we had to go through what is a Turing machine, right? And then we used the von Neumann cellular automata kind of an example of this philosophy put into practice, okay? I want self-reproduction. I do this through Turing completeness, and so I construct my CA in this way. And then, okay, related to this part, because it was also about theoretical stuff, mathematics, it was the KdV equation, which was separated from the rest to not overload you with math and lose everybody after the fifth course. And yeah, so this was the first part, so more theory. Then the second part was more practical again, a little bit of theory in there. About basic or historical life models. So in this case was the elementary cellular automata that Wolfram studied, then the game of life as an example of a 2D CA, the Baricelli cellular automaton, the first one which was simulated on a computer, and then the reaction diffusion, which was the first continuous models. So these are they're still alive today, these models. People still study them, except this one, which kind of was lost to time. But they're legacy. Okay, they were invented a very long time ago. They still have some relevance, but they were kind of the old school models. And then the third part of the course was again practical, and it was a look at the more modern Alive models. So most of those were from the year 2000 and on. And so the main example of this was Lenya, the neural cellular automata, and the agent-based models. And so here I have the first question on Slido that I want you to answer is just to get a feeling, what was the part that was most interesting to you? So I never tried this thing. I think you should rate the three parts from best to worst according to you, just to see what people think. So I think it should be live. Yeah. Let me show you the code again. Okay. How many are we doing? Okay. Let me forward, and then we'll look at the results when everybody voted. Right. So this is what we did in the course, and so this, as far as I know, at least, covers a big part of the artificial life field that I know, right? Because I don't know about all the fields of Alive, since Alive is so interdisciplinary. Of course, there are some things I missed. So some other possible subjects that could have been treated in the course or looked at are one that was actually that was a course last year when Clément gave the course, was I look at the blockchain as an artificial life system. Okay, so this is an interesting example because it's an example of something which looks like an artificial life system, but wasn't designed to do so, right? So the blockchain, if you don't know, just in a few words, is a system. How can I say that? Yeah, it's a monetary system, so it's a way to kind of keep track of who pays what, which is completely decentralized. So there is not one entity that keeps track of who paid what to somebody. You don't need to trust any single person in order to be able to trust the currency that that you use. Okay, so that's what blockchain does. And the interesting thing is that since you cannot trust anybody, you have to somehow make it so that the behaviors which make the blockchain function are the one that emerge naturally, the one that people engage to naturally. So the way this is done is that you give some monetary rewards to people if they do the good thing somehow. And then the interesting thing is that, okay, you have every single person that does things for their own reasons, which are usually to win some money, right? This is some broad goal that most people have, even if it's not their main goal, right? It's a very good intermediate goal, right? No matter what your goal is in life, it's likely that it's easier to obtain if you have more money, right? So it's a good it's a good thing to have money in any case. So yeah, so you have people say, okay, I'm gonna mine some Bitcoin because it makes me money. Then other people say, okay, I'm gonna trade Bitcoin because it's safer or because of whatever. And then when you zoom out, you see that there is this huge network of kind of mining nodes, checking nodes, etc. And this network is really self-organized. I mean, there is an incredible organization that makes the blockchain function. So that's an example of kind of emergence of complexity from simple rules. Like the rules of the blockchain are more or less simple. Okay, you have your wallet, you're allowed to mine Bitcoin by solving these difficult problems, and then you get rewarded. And then you can submit transactions. And just with that, you kind of construct the trustless monetary ecosystems emerges from that. Okay, so that's an interesting thing. The problem with studying this in the artificial life course is that blockchain is in itself not a very easy thing to understand. So usually what happened last year is that the course on blockchain as a life system became just a course on blockchain. And so that was not the goal. Right. And so related to this, there is another interesting thing. So I will link to this, a very interesting video on YouTube about this, is the subject of this game theory tournament. So what do I mean by that? So people in game theory, they organize these tournaments where essentially you have a game, which is a very simple game. Two players play this game. So you can either choose to cooperate or defect, it's called, which is not cooperate. And according to the decision of the two players, you win some money or more or less money, right? So usually what happens is that if both people cooperate, they get like $3. If one cooperates and the other defects, the cooperator wins 0 and the defector wins a lot, like 7, let's say. And if both don't cooperate, they win just 1, let's say. Okay, and so this is not too interesting per se when you have just two people competing, right? You can compute the Nash equilibrium and you see what is I mean, it's also interesting to see what happens, because the optimal play is just to defect, even though it's not what gives you the best reward. But what's interesting to see is what happens if you put a lot of these agents that play this game and you play a tournament. So you select 2 agents at random, you make them play together, then continue like that. And what you see is you have some strategies that are better than the other. And it's quite surprising because you see that you have an emergence that strategies that cooperate more tend to do better in these tournaments, right? So this is kind of interesting because it kind of it's somehow the emergence of cooperation, right? Just like as in real life, in practice, the cells had to cooperate, right, to create these big organisms. So it's related in a life in this sense. So this could be an interesting subject, but I don't know enough about it to give a course. But I will link a video which is very nice on this. Then, of course, other things we didn't cover is wet artificial life. So remember, wet artificial life is the one which actually happens in the lab, and it's usually chemistry or biology based. So this exists in some minor, of course, it's much harder to do wet alive than soft alive, right? In one, you just need a computer with that you can code on. In the other one, you need a full chemistry or biology lab to do it. But it does exist, so people do experiment in this. Then you have hard artificial life, which is robots. So this one is also quite rare. So we'll see after how the different kinds are distributed. But it's usually done. It's because it's usually done by simulating the robots on the computer, right? Because it's more cost efficient. So you do have people working on kind of robotics swarms and stuff like that, which is related to artificial life. They usually do it on a computer with the simulated robots, so it kind of falls back to soft A life. But that's something that you don't talk too much about, and I don't know much about it actually. Yeah. Then you have another big subject, which is also tangential. It's artificial life used for generative art or video games. Okay, so this, in a sense, all of the things we presented can be used like that. Usually, these artificial life models, the rise of complexity gives interesting things to look at, but sometimes it is done really for this purpose. So this we've seen a bit with Boids. I said that the Boid simulations were used a lot in like, I don't know, Disney movies, Pixar movies to simulate the flock of birds or fish. But you have people really doing like, using this emergence of complexity to create things that are beautiful to look at. So the goal is very different. You don't want kind of reproduction or evolution. You just want something that becomes nice to look at. And the cool thing is that whenever you find, let's say, a set of rules which usually produce nice things to look at, then you can play with the parameters and you get a huge range of cool things. So that's the advantage compared to traditional art, which is not generative. Then, yeah, I can say more general topics about open-ended evolution. So this I presented in the first few courses, what is roughly open-ended evolution. I didn't mention it too much after that. It's mainly because, yeah, it's very hard. I don't know of many works that work really on this edge. It's kind of a byproduct of emergent complexity. Yeah. And finally, another thing which is somewhat related to a life. It's more related to real life than a life, but it often pops up in the artificial life paper is evolutionary and genetic algorithms. Okay, so these are machine learning algorithms that are used to learn, to train some machine learning model, and they're inspired from real life in the sense that, okay, you simulate essentially some evolutionary procedure to select the best performing algorithms. And so in that sense, it's somehow related to artificial life, but kind of from afar. So yeah, so let me look at the answers for the first poll. Okay, so actually it's pretty somewhat evenly distributed. So I take this as a good sign that the three parts were were good. And then another question, okay, this one I'll just ask like this. I leave it open if you think about something. This is a text answer. And so the question is, do you think there is some subject I missed or some subject that you know about that I didn't mention? I would be interested to know if you know some alive model or some part of alive that I haven't mentioned. Okay, this is really a shot in the dark. If you think about something, write it, but otherwise. Or you can also tell me, you don't have to write it on the slide. Okay, so this is for the recap. And one thing that I wanted to do is to take a look at the papers of artificial life that are coming out kind of right now. So the best thing to do this, as far as I know at least, is to look at the ALIFE conference. So this is an artificial life conference that happens every year. I think it's the biggest one, right? It's probably, yeah. So it's the biggest artificial life conference. And so what I did is took all the abstracts of the papers that were accepted last year and did more or less heuristic division in different subjects of artificial life. So here we see what I found. Okay, this is approximate. It's not clear. I just read the abstract and decided which part it belonged more. So as we can see, soft artificial life, kind of unsurprisingly, is almost half of it. Then you have a bigger part than I thought, actually, of wet ALIFE. So these are papers which had actual experiments, either chemistry or biology experiments. So for example, one that I remember is the people did some experiments with goldfish, actually, to see how they respond to predators and stuff like that. That was pretty interesting. Then hard artificial life, very, very few papers. So there are only 2 papers where they actually had a robot, a physical robot, and did stuff with it. But of course, as I said, hard life is often kind of absorbed by the soft part because people just simulate the robot instead of building them. Then you had a big part, and this is interesting, 18% of machine learning techniques or kind of algorithms more generally inspired from artificial life. So remember, for example, this ant colony optimization stuff of this kind. So this is interesting because, yeah, you see really that artificial life is coming very intertwined with the field of machine learning. And this is not very surprising because, of course, I mean, 50% of ALIFE is software. So now a lot of software is a big subject in software is machine learning. So this is true. But these are papers which were not strictly ALIFE. They're either applications of artificial life ideas to machine learning techniques, as I said, like evolutionary algorithm or genetic algorithms, or or application directly of machine learning to some ALIFE problems, but that was rare. Then you have a relatively big portion of theory. Okay, so the theory, you have to put a little star on it because it's not, when I say theory, I just say that there were mostly no experiments. It was just kind of equations and reasoning on equations, but it's not math. Okay, it's let's say it's math, but it's physics level math. Okay, so I'm a physicist, and it's not an insult, but it's not rigorous math. It's kind of, there are deductions, but they are deduction in the way that a physicist would do them. So you don't go into like a theorem proof. You just kind of put some general things that looks okay. And that's perfectly fine for me. As I said, I'm a physicist, so don't take this the wrong way. It's just to characterize the theory. I said most, okay. There were some, I think, that were kind of more rigorous. And then the last part is, I don't really know why it's in the ALIFE conference, but it is, and it's some papers of which the subject is kind of medicine or biology or chemistry, with an application usually of a machine learning technique. So there were some kind of the development of cancerous cells. Okay, I don't know exactly what he was talking about. Okay, you can say that it's kind of related to ALIFE because, I mean, the tumor is some sort of living system. And so, yeah, so that was also a relatively big part. So this is kind of the papers that came out of artificial life, just to give you an idea. And yeah, so just for the numbers, so there was approximately 110 papers which were accepted, probably submitted around 200, 250, probably something like that. So it's not that small, but it's still, okay, if you compare it to the biggest field that there is right now, you can compare it to machine learning, where in the biggest machine learning conference, you have usually 3,500 accepted papers. Okay. But okay, this is the biggest field there is right now. So yeah, another thing to note, which I already said, I think, is that you have a lot of this use of machine learning methods in artificial life. And I think this is a good direction to have. Okay, I think that the machine learning methods are a promising direction to apply in artificial life, as we'll see later when I talk about what we are doing. And the last thing I wanted to mention, just in case it interests you, there is a good portion of the papers which are not full papers, they are preliminary results papers. So they are very short, usually it's 2 pages or 3. And they present very shortly some preliminary results. So for example, people build some smaller life systems, they get some interesting behavior, they describe the system quickly, they describe the behaviors they observe, and that's it. And so if, okay, let's say, either because of the project or for some other side project that you have, if you have a small artificial life project with some results which look nice, you can also try to write a 2 or 3 page paper, send it next year, and you never know. And especially because next year it's in Japan, so that's a nice thing to keep in mind. But yeah, so the barrier of entry as of right now, it's not too high. So you can actually, I mean, and that's people what they do is that, yeah, that's another thing they need to say is that I don't know what's the percentage, but a lot of the people in this Alive conference are actually doing it on the side, right? They have their job and then they have their small Alive project and they participate in Alive each year developing their project. So it's, yeah, the barrier of entry is not that high right now. Okay, so that was for kind of, yeah, the artificial life papers. And as a last thing, yeah, in 20 minutes, I wanted to give a light overview of what we do in, I mean, I am in between 2 labs, but what we do concerning Alive research in this lab. So the main, at least for me, the main axis of research that I want to work on and I'm working on is this search of complexity. And more precisely is to try and scale up the detection of complex system in artificial life, of emergence of complexity, okay? Because as I said many times, I think one of the problems right now in artificial life is that you just have a single example, right? It's life on Earth that so far is the only example where we have open-ended evolution, reproduction, and so on. So if your goal, which is one of the goals of artificial life, is to distill some general properties or principles that tell you whenever you can have the emergence of life, it would certainly be useful to have more examples, because otherwise it's really hard to test your theory or even come up with a theory, right? So right now, the way that people came up with examples, although they're not ideal examples, but the way they do is you make some artificial worlds, and you collect those which are successful, okay? And the way that people collect the successful artificial worlds is by human intuition, right? They look at the dynamics and they intuitively see, okay, this one looks interesting, this one does not. Sometimes you can go a posteriori and find some metric that validates this intuition, but the first step is usually a system is complex and interesting if it is complex and interesting to us, right? So this seems to work pretty well. I mean, all the systems that I've presented today, most of them, some were trained, but they were found like this, right? People just used human ratings, maybe with some combination of automation for generation, but yeah. We are ultimately the determining factor on whether something looks interesting or not. There is no other criterion which works as well. So if you remember in the elementary CA course, I asked you, what of these 3 histories looks the most interesting? And the vote of the people were pretty aligned with what is actually considered theoretically interesting, in the sense that this automaton is actually Turing complete in some sense, and the others are not. So the problem with the human preference is that it doesn't scale. Okay, you have to actually look at the video and say if it's cool or not. And so what we're trying to do is to see if you can use potentially some machine learning with some machine learning tools. Oh, whoops, sorry. No, sorry. What I wanted to say, yeah. If this method was able to scale, this means that we would be able to have a huge data set of relatively interesting alive models and very different models. Okay, some are discrete CA, some are continuous, some are whatever, agent-based. And so then if you have a very big data set, there exists some machine learning methods that, given just a raw data set with no other information, they try and search for similarities or hidden invariants behind the data. Okay, so one example that I know, I think it's linked here, is in general relativity. Okay, that won't talk to everybody, but you have certain metrics that describe certain spacetimes, and you have a big class. I mean, there is a big class of symmetries of the metric. So if you apply this symmetry on a metric, it will describe the same spacetime, right? So we have a huge class of metrics that describes the same spacetime. And if you just give a machine learning model just a bunch of metrics, not telling him what spacetime each metric describes, and you ask him to find similarities between the metric, well, the machine learning algorithm is actually able to find some hidden invariants, which we know from physics, that determine whether two metrics are the same or not. Okay, so this is kind of the same idea that we could potentially apply. If you have a huge data set of different interesting models, maybe some machine learning algorithm can extract some features which are common to all these models, something like that. Okay, this is the second step. The first step is to make this process scale. And so the idea is that, you have two ways of making a discriminator for interesting or complex things. One way is either you have a good theoretical definition of complexity or kind of simple definition, which you can actually implement in a criterion. Then you can apply that if it's simple enough. Or the other approach is to try and capture our process when we decide if a video is interesting or not. Okay, try to emulate this process. So this is not ideal because it will be biased towards us, right? So there will be some linear bias. It will find interesting what we find interesting. But so far, it seems that this way of finding interesting things is the state of the art. So yeah, more precisely, what I meant to say is that this kind of ideas is what I'm trying to solve right now. Not completely, but find some things that work in this direction. So the first idea is the classification by prediction quality. So this is ongoing research. So the idea is very simple, and I talked to you about it in the ECA course. So if you remember from the Wolfram classification, essentially what it tells us is that what is nice and interesting is things that are neither periodic, right, class 1 or 2, nor chaotic, which is class 3, right? If you are neither this nor this, you're necessarily interesting, according to these classes. So this you can translate it to what is nice and interesting is neither easy to predict, okay? Periodic things are easy to predict, nor impossible to predict, right? Chaotic things are impossible to predict. And so if you phrase it in this way, you can start to see the potential connection with machine learning models, okay? So the idea is that if you train a model to predict the future dynamics of some artificial life model, then by asking the model, you actually get a score of predictability of the dynamics, right? It's just how well the model predicts. And the idea, the generic idea here, is to look for the cellular automata that lie in between perfect predictability and zero predictability. And hopefully these are precisely the class 4-like ones. So this approach, we know that it works if the model, the predicting model, is a human. Okay, that's essentially what we do when we see the dynamics. If it's completely chaotic, we don't understand anything, not interesting. If it's super predictable, super boring, we don't need to see the rest of the video. And so the interesting ones are in between. But the question is, okay, if now instead of a human, you have a machine, it gets kind of harder to make it work. So right now we haven't made it work yet. Then another approach, which is, another approach which is more kind of theory-based. This is just to say that you can look for complex behavior by looking for special regions in the parameter space of the artificial life model, right? So one such class of special regions are the regions which lie at the interface between two phases of behavior of the model. Okay, so this is kind of the picture that you should have. This is parameter space of the model. You have two phases here which have qualitatively different behavior, and you find a special place in parameter space which is the interface between these two. Okay. So why would we expect complex or interesting behavior at this special place? This is very loosely motivated from physics, where you expect scale invariant behavior. So scale invariant behavior in particular is infinitely complex because it means that you have, how do you say, you have features at every scale of the system, right? No matter how much you zoom, you still new features. And so in some way, there is infinite complexity by some definition of complexity. So maybe you would find interesting behavior there as well. And so also, if you have a phase which is a chaotic phase and a phase which is a periodic or non-chaotic region, you would expect, if you can go continuously from one to another, to have some point where you are in between. Okay. So for this, you can read a very small paper that we did with some master students about applying this idea to Lenya. And I think I've already talked about this, but the videos of Lenya that I showed in the course and on the website, they come from the application of this thing. So it kind of works. Then another idea that I wanted to mention is this idea of the arrow of time, which is more or less tangential to artificial life. So this is the paper if you're curious. So what we found is that all else being equal, if you take a large language model and you train it on text, they seem to do slightly worse whenever you ask them to predict the previous word instead of the next word. Right? So usually large language models, the way you train them is that you give them some text, you hide the end of the text, and then you iteratively ask him, okay, what is the next token? What is the next token? And so on and so forth. Right? So this is how you usually trained it, how ChatGPT was trained. And the reason to do it is because usually you want to complete text, right? For a chatbot, you want the chatbot to fill the next answer. But nothing prevents you from training the model to do exactly the opposite. So to predict the previous word in a sentence. Okay, so you can give it the end of a sentence and it fills the words going backwards. And so what we see whenever you try to train the large language model like this is that they do very slightly, so 2 or 3%, worse than the one which is trained in the forward direction. And so we call this an arrow of time in language, let's say. Okay, and the most interesting thing is that if you do this for different languages, different language data sets, it seems to be completely universal. Okay, so it does not depend on the language. Every language displays this kind of arrow of time effect. And at first, this was surprising because the thing that I was thinking is that, okay, maybe there are some languages where in sentences you organize the words differently. So you have the verb first and then the subject instead of the opposite. And that may invert the effect, but it's actually not true. Yeah, sorry. So the y-axis is the loss of the model. so the inverse of the score for the people who are not in machine learning. And the x-axis is just the training. So number of training steps. Yes, I should explain. So the continuous lines are the models trained forward, and the dotted lines are the models trained backwards. And this kink that happens for all the languages is nothing special. It's just that during the training, we just do a restart of the learning rate. We jump it up just to, because it's supposed to make it train better. And so that's why the last jump. But what you should see is just that the dashed line and the corresponding colored continuous line, they are always somewhat translated upwards during all of the training. And so, yeah, another question? So these models, they are medium, so it's GPT-2 medium, so it's around 130 million parameters. No, sorry, 350 million parameters. We also tested it in some way. It also works for about 1 billion parameters. And yeah. And so when you first hear this, when I first heard this, it seemed kind of obvious, right? So if you ask humans to write backwards, it feels much harder than forward. And then if you start thinking at some examples, you might think about, for example, I don't know, let's say jokes, where the setup kind of implies the punchline, but maybe it's harder to go from the punchline to the setup. And so you might think, okay, maybe it's kind of obvious that the language has some sort of direction. But the surprising thing is that if you look at the information content of when trying to predict it forward versus backward, you can actually prove, and it's a very easy proof, you can look it in the paper, that in terms of information content, so how much info you have to make your prediction, this is completely symmetric. So in principle, you have enough information to obtain the same loss or the same score going forward or backwards. So it's not a matter of, yeah, but if you predict the joke backwards, you don't have enough information to predict the setup from the punchline. This seems true, but it's just that the uncertainties in the prediction of the words will be kind of mixed up around. But if you sum all the uncertainties, then they kind of cancel out and it gives the same uncertainty forward and backward. So, yeah, and the other thing is that when you think that, okay, it's obvious it's harder to speak backwards than forward, you would think that if it's harder, it's really, really harder, like 20, 30% harder, 100% harder. But in practice, it's very, very small. Like it's 1 or 3% the difference in loss. So it's slightly harder. So yeah, so what we do is that we conjecture that this difference at a more high level, not for language, this difference comes from the fact that while there is as much information forward and backward, kind of the information is not delivered in the same way. So the typical example that I usually give is that if you have a data set of equation, which is prime number 1 times prime number 2 equal the product of the prime numbers. So if you're trying to predict the next word, it will be easy to learn in the forward direction, right? Because given the 2 prime numbers, to predict the product, all you have to do is do the product. Whereas if you go backwards, of course, if I give you the product of the prime numbers, in principle, you have the necessary information to guess the 2 prime numbers. But this information is much harder to get because you have to factorize the number. Okay. So this is some effect related to that. And so what we conjecture for language, why is it universal for language? Since then, we tested even 3 more languages and it works every time. Is that this difference arises because the language is somehow made, or the language is, evolves, such that it is an efficient way to communicate, and we communicate in the forward way, right? We put one words after another. And so the idea is that if we design a language to be easily understood in the forward direction, we don't show. There is an analogous setup that we prepare. This implies that it will be harder for the backward direction, okay? One example that I can give before going forward is that if you take a matrix which is sparse, so a matrix which is mostly zeros, if you invert this matrix, it will typically be much less sparse. Okay, so this is kind of the same idea. If I prepare a matrix which is simple, if I want to kind of invert this matrix, go the other way around, it will naturally be less simple. And we think it's kind of the same thing for languages. We're not sure. We have a toy model where we show this, but yeah.
How do you pull apart the difference between, like, the one factor is how the language is evolved or designed?
Yeah.
The other factor is how people actually use the language, right? So maybe
Yes.
when you're training, your focus is always human-produced text.
Yes,
So
exactly.
maybe it's when humans produce text, they produce it such that
Oh, yeah, certainly. Yeah. When I say the language, I really mean the way that humans use the language.
because I mean any language is probably ways to express sentences all back.
Of course. Yeah, of course. So what I mean is that the way that we use the language, or the way that the language is used, has kind of this emergence of the era of time. But yeah, if you want more info, look at the paper. It's very like cleanly written. It's really easy to read, I think. So this is kind of a big tangent. This is something that actually Clément and Jérémy stumbled upon, and then we just did all the necessary experiments to validate it. It's not directly related to a life, but it is somehow. So why? Because this era of time that emerged, to find this era of time, you don't need to actually understand the language or the signal that you are working on. Okay, so this could be an example of a technique that is used to detect the presence of a potentially intelligent signal, or at least a non-trivial signal, without knowing anything about the signal, right? If I don't know anything about Vietnamese, right? But I can still kind of, since I find this era of time that also I find in French and in all the other languages, I can kind of, this is the angle that we have in the paper, that the existence of an era of time implies the existence of some complex processing of the information of this signal. Okay, this era of time is there because people use the language to communicate ideas and so on. Okay, I'm not sure this is true, but this is one example. And so one thing you can think about, a kind of sci-fi application of this, you get some random radio signal from space, and you don't know if it's really a natural signal that just was produced maybe by some, I don't know, some star exploding or something like that, which might not look random, right? It doesn't mean that it has to be completely random. It could be not random, but still not have any sign of intelligence inside it. And so one could say that you could test for the presence of an era of time. And if the idea that the era of time is related to complex processing of information, then you might detect if it contains some intelligence behind it. Okay, so this is the kind of ideas that we would like to apply to find complexity, some sort of things you don't know anything about the signal, but you still can extract something by using some machine learning methods on it, right? Okay. So a few last things. One other direction which I want to try, I already said this during the NCA, I think, or the Lenya, but it's human preference, but faster. So the idea is very simple. So as you remember, for Lenya and the MNCAs, how did the people do to find all these interesting rules? Well, they applied some very human-driven reinforcement learning or genetic learning, right? They produce 100 videos. They rank or they select the 20 best videos. They take it, they mutate it, reproduce 100, selects the 20 best, and so on and so forth. And so this is good, but it's very slow because you have to ask a human, and it's very annoying to do for a human. And so the idea here, it's very, very simple. It's not a new idea or whatever. Is just to teach a neural network the hidden fitness function of what is interesting for a human. I think it's impossible to capture it perfectly, but maybe if you capture it good enough, you can get some nice results. And so this is an example of, I think, one of the first paper where this method was introduced. So their goal was to use reinforcement learning to train this stick to do a backflip. Okay. So of course, this is very hard because what is the fitness function for what is a good backflip? Okay. If you want to write it, you kind of have to say, okay, then you have to have a non-zero angular momentum, then you have to fall back on your feet, so you can start putting terms which check for it and gives you a score, but it's very hard. Okay, it's very different from the case of the Carl Sims evolved creatures. When you want a creature to go from point A to B, there the fitness function is super simple, it's just the distance to the target point. And so what they do here instead is that they don't know the fitness function a priori. They just ask humans, given 2 videos of backflips, to say which one is closer to the backflip. And then there is a neural network behind this that learns the human preference function, which is unknown. And so what's nice is that to train this backflip, so this reinforcement learning algorithm, you only needed 900 human annotation, they claim. And this is exponentially lower. It's not a good way to use exponentially, but it's substantially lower than the amount of gradient descent steps that you need to do on a reinforcement learning algorithm. In reinforcement learning, you usually need millions of examples. Okay, so this would not have been possible by having a human just manually label everything. And so all that I want to do is just do the same thing, but with what is interesting in Lenya, for example. Another thing was sexual reproduction in NCAs and diversity in NCAs. So yeah, the idea was to enhance the neural cellular automata with a bit more capabilities to make them closer to a system in which you can have evolution or at least more diversity than just one image. So I don't know if I already showed this. So this was a paper also from the last artificial life system where they trained an NCA to reproduce. So you see that you have the egg, you train to get into a fish. Then you have a second training step where you get the fish to lay an egg, right? And so this is the final step. And then what they do is just that they make some surgery. So they take this egg and they put it into a new world, and then they let it evolve. That's what happens here. And so if you look, this is the final fish. Yeah, okay, I won't be able to get it great, but you see that during this part, because the egg is not perfect each time, you get some gradual mutation of the shape of the fish. But I wanted to try something of this kind along with this DNA idea that I told you, where you can actually add some DNA channels into the creatures. And then if you get creatures with mixed DNAs, they actually get a mix of the properties of the parents, right? So this is the child of this and this. You can see it's kind of a triangle, but also a rectangle, and it's in between red and green. This one is a round rectangle, which is bluish, and this is a roundish triangle, which is purple. And so, by the way, yeah, so the way I trained this, I really trained the NCA only to make these 3 shapes. I never trained it to make the hybrids. These are completely emergent from the dynamics. And then if you put just random DNAs, you get some random combination of these 3 things. And so you might think that if you combine this with a sufficient kind of set of primitives and this sort of reproduction with eggs, you might actually get something where you have some evolution of the creatures in your NCA. Another direction for research is more rigorous Turing machine cellular automata. Okay, so if you remember from the Turing machine courses, there was some haziness on what does it mean for a CA to be Turing complete. Right? We had this input and output functions on top of our CAs, which told us how to take the Turing machine and its tape, convert it into a CA configuration, then let it run, and then convert it back to the final tape. So you might ask, okay, what if the input and output transformation, they actually do the full computation? Okay, you might say that the input would be just run the Turing machine, set it into the CA, do nothing with the CA, and then read it back. So the question is there a way to define more rigorously and naturally what are the allowed output and inputs, roughly? And how does it change the definition of Turing completeness? Do we still have that all these CAs are still Turing complete, or it's actually much more stringent? Okay. So for more info, you can ask Barbara, which is working on this more closely and knows more about this than me. And yeah, and finally, just to conclude, is just the creation of random alive models, following some principle, for example, physics or Turing universality. We construct some models from scratch. So this is one example that a student, Eugène Bergeron and Clément, are working on. So this is a continuous alive model. So you can see the particles can move continuously, where they connect, and then you have some discrete cellular automaton dynamics on top of this kind of connected grid. So it's a combination of a continuous and discrete CA, which with the goal of trying to make something which is Turing complete in a continuous setting. And this is a video of another project that we had with a physics student and Joao, a physics professor, where we tried to design, this is how do you call it? This is an LGCA, a modified LGCA, where we try to get inspiration from the elementary particles from physics to get something nice. We didn't get something very nice, but we did get some interesting stuff. And yeah, so I think that's it. So some closing words. I wanted to put some closing words, even if I was not very inspired. So the goal of this course really was to give a broad overview of the field of soft A-Life, and at the same time giving some hands-on dives into specific models to see really how people do actually implement these things. And so for now, the field of A-Life is still, we must say, it's still a small field of research. Okay, for example, there are not a lot of permanent positions for A-Life, even postdocs, it's very rare. But it seems to be growing relatively rapidly. Although some of the growth might be just because it's related to machine learning and machine learning is exploding, but I don't think so. I think it's still growing in itself. And so I tried to put a final phrase here, and I said, yeah, so there seemed to be a great mismatch between the size of the field and the general interest in the subject. Okay, so for example, when I talk to people about this field, coming from physics, computer science, biology, etc., people seem very interested into the premise of the field, but it's either not very well known or for some reason it does not translate into actual research for now. But I think that this tension must be resolved at some point. And so here I had no idea how to end this phrase. And so I went to ChatGPT and asked, okay, can you give me some completions? And they were all garbage. And so I said, okay, make it funny. And it was actually funny. So I just put the 5 examples that it gave, and I'll let you read those. And with that, yeah, I think that's pretty much it. So I remain here for questions, and otherwise, see you next week for the projects. Okay. Thank you.